In this unit, we're going to build on the last couple of topics, which the last couple of topics were where we discussed the nomenclature of alkenes. Now we're going to go into discussion of the stereochemistry of alkenes and how we would incorporate descriptions of stereochemistry into the name of alkenes. In this particular segment, we're going to focus on the so-called cis and trans way of designating stereochemistry. In the next segment, we're going to focus on an alternative method for designating stereochemistry of alkene groups, which is called the EZ notation. So focusing on cis and trans here, I want to remind you first and foremost that the reason why we need to specify the stereochemistry of alkene groups is because if we think about a carbon-carbon double bond relative to a carbon-carbon single bond, and most carbon-carbon single bonds, there's relatively free rotation around the bond. On the other hand, at a carbon-carbon double bond, there is no free rotation. In other words, the atoms are locked into place in that trigonal planar shape, however they are oriented here. So the two structures that we have shown on the left and the right, those would be different stereoisomers of one another, because if we look at them both, they have the same IUPAC name of 2-butene, but they differ in how those atoms are oriented into space, and due to the fact that we can't rotate freely around the carbon-carbon double bond here on the right or here on the left, those molecules are essentially stuck in that particular configuration. And so we need a way to refer to those specific configurations within the name of a molecule so that we will know what stereoisomer we are discussing, since different stereoisomers can have very different effects, for example, in terms of their biological properties, how they would interact with a biological system such as a protein. So we're going to focus on the so-called cis and trans way of designating the stereochemistry of alkene groups here. The cis and trans designations of stereochemistry are usually reserved for the relatively simple alkene molecules that have just one alkene group, and these are typically reserved for molecules that are exclusively hydrocarbons, molecules that don't have a bunch of other functional groups in them other than just the alkene group. So we're going to take a look at the difference between cis and trans and how we define those two terms. So if we look at the term cis, what the term cis refers to is that the two bonds of the main parent chain that lead away from the alkene group are on the same face of the molecule. So I'll illustrate this with an example. If we follow the parent chain here, we'll go back to that example of 2-butene. Following the parent chain of 4 carbons, 1, 2, 3, 4, we see that relative to the carbon on the left, the parent chain goes down. Relative to the carbon of the alkene group on the right, the parent chain also goes down. And so we describe that as being cis. Cis meaning same. The two bonds coming off of the alkene group are going on the same direction, off on the same face of the molecule. So when we describe a molecule as cis, what we're saying is that relative to the parent chain, remember that the parent chain is the longest carbon chain that contains both of the carbons of the alkene group. So relative to the parent chain, the two bonds leading away from the carbon-carbon double bond are on the same face of the molecule. On the other hand, we can also refer to the so-called trans stereoisomer. And the trans stereoisomer, I'll go ahead and draw that for the 2-butene molecule. And then the 2-butene molecule, to make this into the trans stereoisomer, we again follow the longest carbon chain here, which in this case is pretty easy. We'll do a couple of more complex examples in a moment here. And then we look at the carbon on the right here of the carbon-carbon double bond, and we see that the bond to the next atom we have to go upward to get there. On the other hand, if we come to this carbon on the left side of the alkene group, we have to go down to get there. So these two bonds are going off to opposite faces of the molecule, and so we describe that as being trans. So the definition of trans is that Relative to the parent chain, the two bonds leading away from the carbon-carbon double bond are on opposite faces of the molecule. One going up, one going down, or one going left, one going right, depending on how you have the molecule oriented. They're going in opposite directions. So I'll go ahead and write that out for you. Relative to the parent chain, the two bonds that lead away from the carbon-carbon double bond are on opposite faces, hence trans. Okay, so let's apply these concepts of cis and trans towards some more complex examples where we will have to first find the parent chain, come up with the IUPAC name, and then assign the molecule as cis or trans and incorporate that into the name. So let's go ahead and do that with the following example problem. All right, so let's take a look at this example problem. First things first, we're going to come up with the IUPAC name for this molecule, and then we're going to designate stereochemistry since the directions here say to include stereochemistry in the name. When we're specifying cis-trans stereochemistry, we'll put it at the very front of the name, and we'll use a hyphen to separate the term cis or the term trans from the rest of the name. So let's go ahead and look for, to start off here, the longest carbon chain that includes both carbons of the carbon-carbon double bond. So we have a couple of different options that I see here. We have the option that I'm going to highlight out in green here. So we could start here, running through the molecule up to here because that's the longer pathway. So that's one possibility, and that gives me a total of 7 carbons. And then I also see an alternative route here where we could go the route that I'm mapping out in red here. 1, 2, 3, 4, 5, 6, 7. So that would also be a 7 carbon chain that we've highlighted here in red. So we have to decide which of these carbon chains is the correct one to use. And the one that is the correct one to use, is going to be the one that has more branches. If we go back to that sheet about nomenclature, the indication there at step 1 was if there's a tie about finding the longest carbon chain, go with the one that has more branches. So the path that we've mapped out in green there would have 3 branches coming off of it: a methyl branch, an ethyl branch, and an isopropyl branch. The path we've mapped out in red, on the other hand, would only have 2 branches coming off of it. That would be 2 isopropyl groups. And so therefore, the proper way to label this is going to be through the green route. So we'll go ahead and label it through the green route. We're going to number our carbon atoms there, 1 through 7. We're going to start at the end closer to where the alkene group is. Remember, the alkene group takes priority in deciding where to start numbering. So we'll start numbering from this end at the left. 1, 2, 3, 4, 5, 6, 7. So we've got our parent chain there in place, and then we need to specify the names and locations of those 3 branches in alphabetical order. So I'm going to go ahead and place my name here for the 7 carbon chain. It has an alkene group in it, so it should be referred to as heptene. And remember, we have to indicate where the alkene group is, because if we move the alkene group to different spots of the chain, we'll get different constitutional isomers. We want to be confident about what we're referring to here. So this is 3-heptene because the first carbon of the carbon-carbon double bond is there at position 3. The alternative name that would also be totally acceptable to this would be hept3-ene as an alternative there. So that's totally fine as well. Okay, so now we need to go in and specify our branches. Our branches, I'll go ahead and highlight in blue: methyl, ethyl, isopropyl. So plugging those in alphabetical order, I'm going to put the ethyl branch first. That's at carbon 3, so I'll do 3-ethyl. And then isopropyl comes next in the alphabet, so 4-isopropyl. And then last but not least is our 2-methyl group. And then finally, remember that we were instructed to include stereochemistry in the name. So to include stereochemistry in the name, since this is referring to the cis or trans stereoisomer, we have to look at the alkene group and ask yourself, when we follow the parent chain, that's the chain we've highlighted in green there, if we look at the carbon atom of the alkene group on the right, we have to go upward to get to the next carbon of the chain. If we look at the carbon atom on the left, we also have to go upward relative to that carbon to get to the next carbon in the chain. Remember, we're always following the longest carbon chain here, so that's your anchoring point there to decide whether you're going up or down. You're looking at the carbon atom of the alkene group and then ask yourself, following the parent chain, do you have to go up to get to the next carbon of the parent chain or down? And in this case, it's up in both directions relative to the carbons of the alkene, and therefore we describe this molecule as being cis. Hence, I'm going to put here at the very front of the name, cis, separating numbers from letters using dashes, dash, 3-ethyl, etc., etc., etc. And you could have also, to give you just one additional way of naming this, rather than calling it an isopropyl group, you could have also referred to that as a 1-methyl ethyl group instead. That would certainly affect your alphabetization, but you can do it that way if you like. So let's do one more example to make sure that we have the hang of this designation of molecules as cis or trans. I'm going to go ahead and put up an example problem. I encourage you to hit pause, try to work through it on your own, and then hit play to see if you got the right answer. So here we're tasked with another question. We're asked to provide the IUPAC name of the molecule, including the stereochemistry. First things first, let's find the longest carbon chain. Looking through to find the longest carbon chain, and remembering that that longest carbon chain that we find has to include the alkene group, I find the longest carbon chain to be coming through the molecule like so. Keep in mind here at the lower end of the molecule that it would have been fine to choose going in from this direction as well from the right-hand side, because those two groups are symmetrical. We have two methyl groups there at this bottom end. So you could have started from the lower right or lower left. Either way, you're going to come up with the same name for this molecule in the end. So let's go ahead and number this longest carbon chain. We need to start numbering from the end closer to the alkene group. So looking through here, what we see is that if we start numbering from the bottom end, we come up with the 1, 2, 3, 4. If we start numbering from the top end, our first carbon atom that's part of the alkene group, we go through 1, 2, 3, 4. We come up with a tie there that numbering from either end results in the alkene group being at carbon 4. So which is the correct end to start numbering from? Well, if we have a tie, the tiebreaker is which numbering from which direction is going to give us a branch closer to the end. So if we number from this way, at the bottom, we have a branch there at carbon number 2. On the other hand, if we start numbering from the top end, our branch isn't until carbon number 3. So let's go ahead and we will number based on the blue numbering system, because that is the numbering system that corresponds to putting a branch closer to the end. So always the first thing we look for is putting the alkene group as close to the end as possible. If there's a tie, which there was here, then we go with the end closer to a branch. So the end closer to a branch was starting there from the bottom, so that's what we did. So we came up with 8 carbons in our longest carbon chain, so the parent name of this is certainly going to be octene. And our carbon-carbon double bond starts at carbon 4, so we call this 4-octene, or alternatively oct-4-ene would be an acceptable name for this, for the parent chain. And then we need to specify the names of the branches coming off of this, and this is a branch extravaganza going on here. We have 2 methyl groups that I see showing up, branching off at carbon number 2 and at carbon number 6. And then over here, hopefully you recognize this as a tert-butyl group, or alternatively a 1,1-dimethyl ethyl group. And then over here you have your isopropyl group, or alternatively we could refer to that as our 1-methyl ethyl group. So we're going to plug those in as prefixes into this name. So we'll go ahead and do that, putting them in alphabetical order. So based on alphabetical order, thinking about isopropyl, tert-butyl, and methyl, I'm going to go ahead and plug this in as 5-isopropyl, 2,6-dimethyl, because we have 2 methyl groups in there, 4-tert-butyl, 4-octene. And I will warn you that when alphabetizing, we always alphabetize based on the term iso, but with the term tert-butyl, there is some disagreement in the literature where sometimes tert is ignored when alphabetizing. So I would accept it either way. If you ignored the term tert there, that would be okay. If you include it, that's fine as well. But we've done one acceptable way of alphabetizing this terminology here and specifying the locations of each of those branches. Now for the last part of coming up with the name, and that is assigning the stereochemistry of this molecule as either the cis or the trans stereoisomer. So thinking about whether it's the cis or trans stereoisomer, what we have to do, remember, is look at the parent chain and focus on those 2 carbon atoms, the alkene group, and ask ourselves, what direction does the parent chain go relative to each of those 2 carbons? So following the parent chain, which is yellow, we see that we're going to the right relative to carbon number 5 there. Relative to carbon 4, we're also going to the right. So we would describe those 2 bonds, the 2 single bonds that we're showing with arrows there leading away from the alkene group, as being in the same face of the molecule. They're both oriented to the right. They kind of make a bowl shape is what I look at that and think of, is that since they're both oriented in the same direction, you kind of think of those red lines that I've drawn as forming a bowl. That's one way to remember this, is that the cis configuration looks like a bowl when you trace out those 3 bonds. So we would definitely refer to this as the cis diastereomer of this particular molecule. In the next segment, what we're going to do is expand on this concept of specifying the stereochemistry of molecules to include some new terminology called the E and Z configurations, or the EZ terminology. The EZ configuration terminology is typically used for molecules that are more complex, meaning molecules that have additional functional groups beyond just an alkene. And they're also, EZ is typically the way of designating the stereochemistry of if we have multiple alkene groups present within the molecule. So stay tuned for that in the next segment.